Okay, so we're going to pick up from where we left off and work through a couple of examples on how to do this. If I'm looking at the list of things to know and things to do, this would cover the idea of this first example is finding the sum difference product quotient composition for specific inputs. That's what we're doing with these first couple examples right here, like f plus g of 2. So our specific input is 2. So our definition of addition says f of says f plus g of x is equal to f of x plus g of x. So f plus g of 2 would become f of 2 plus g of 2. F of 2, 3 times 2 minus 2, 3 times 2 minus 2, plus 2 cubed. I like to use the grouping symbols to make sure, just in case I have any negatives that are going to be in there and I want to make sure things distribute properly. So 3 times 2 is 6, 6 minus 2 is 4, 2 cubed is 8, so that would be 12. So f plus g of 2 is equal to 12, specific value. Similarly, f minus g of 1 would be f of 1 minus g of 1. F of 1 is going to be 3 times 1 minus 2 minus g of 1 being 1 cubed. In this particular case, 3 times 1 is 1. Sorry, 3 times 1 is 3. 3 minus 2 is 1. 1 cubed is 1, so that gives us 0. So f minus g of 1 is equal to 0. By the way, a little note, just to make a connection. Oh, that is going to be a point where x is equal to 1, y is equal to 0. That, for us, is an x-intercept. One of our important points whenever we're working with functions. Just continuing some examples, the same functions, continuing the operations. F times g of a half would be f of 1/2 multiplied by g of 1/2. F of 1/2 would be 3 times a half minus 2 times 1/2 cubed. 3 times a half, 3 halves, minus 2 is going to be negative 1/2 multiplied by 1/2 cubed. 1/2 cubed is going to be an eighth. So f times g of 1/2 is going to be equal to negative 1/16. F divided by g of negative 2 would be f of negative 2 divided by g of negative 2. 3 times negative 2 minus 2 over negative 2 cubed. 3 times negative 2 is negative 6. Negative 6 minus 2 is negative 8. Negative 2 cubed is also going to be negative 8. So that is equal to 1. So f divided by g of negative 2 is equal to 1. So there's an example of what I said about finding the sum difference product, but not composition. We didn't get there yet, for specific inputs. So that is where we're there. The second example we're going to do is going to be doing it generally. You'll notice here on example 2, I have 2 new functions, f and g. But the problems that we're going to have, there's no number in there for x. And so really our task is to write a new function. Write a new function from the old function. An example of this that we'll see in class is that the profit of a company is when you take your revenue, how much money you bring in, and subtract from it your cost. So we would say that the profit function is a new function built on 2 other functions, cost and revenue. And we'll see that in class, just to give you a heads up on an application there. So f plus g of x, according to our definition, can be rewritten as f of x plus g of x. F of x is the square root of 4 minus x squared plus g of x, which is 3x plus 1. Looking at this, I'm just going to do a little cleaning up here. I'm going to make it 3x plus 1 plus the square root of 4 minus x squared. When we handwrite expressions with radicals, we tend to like our additions and subtractions to come first, so there's no ambiguity. But it doesn't look like it can do much simplifying there. So that's just a new function. That's what it is. For the subtraction, f of x minus g of x would be equal to the square root of 4 minus x squared minus. Now here's a case where those grouping symbols are going to be important. If you write minus 3x plus 1 without the grouping symbols, you would not distribute the negative to the constant term of 1, and you would not have the proper signs or the proper function. This becomes a square root of 4 minus x squared minus 3x minus 1. And I'm going to do the same rearrangement here that I did previously. Note that there is a positive, a plus in front of the radical on the rearrangement, because up here, this is a positive square root that's implied there. Looking at it, can't do any simplifications on it, and so that is what it is. So we just leave it as it is. But that's how you do it. If there are like terms and distributing stuff that I could do, I would do it, but in this particular case, I can't. Continuing with multiplication and division, so I would have the square root of 4 minus x squared, that's my f of x, times my g of x, 3x plus 1. And I don't know, I suppose that if I look at this, I could do some distributions and make this 3x times 4 minus x squared plus the square root of 4 minus x squared. But I'm not sure if one version is particularly better than the other. In this particular case, there are a couple of awkward functions that just don't combine very well. I suppose at this point I'd accept either one. And then f of f divided by g of x would be, let me change colors here, f of x divided by g of x. My f of x is 3x, no, my f of x, sorry, is, my f of x is the square root of 4 minus x squared. My g of x is 3x plus 1. No simplifying to do, no radicals in the denominator, but I have to make sure, and this is where things get tricky, this is a real heavy point of emphasis, I have to make sure that my denominator is not equal to 0. Generally, I don't have a problem with 3x plus 1 equaling 0, but now since it's in the denominator, I can't allow it. So maybe I'm going to extend my page here, do a little bit of scratch work. I'm going to say, okay, 3x plus 1 equals 0. So 3x is negative 1, and x equals negative 1/3. So I have to say up here that x cannot be negative 1/3. Whether I write it as an equation or an interval or something like that, but I have to say that x cannot equal negative 1/3 so that I do not end up with a 0 in my denominator. Whenever you are working with a division of functions, you must do that every single time. You have to do that. And that's really where people kind of get tripped up there. All right. So those are the functions, how to find them. The one piece that we haven't done yet, oops, that's not going to be good for us. Let me put everything back in order here. All right, much better. And okay, we haven't found the domains yet. Now, what is nice is that I don't have to find the domain 4 times, because the domains of f plus g of x, f minus g of x, and f times g of x, and for the most part, f divided by g of x, are generally all the same. Except for division, which we got to watch out for that 0 in the denominator. So I don't have to find the domain 4 times. I only need to find the domain once. And what we said in the previous video was that all I need to do is find out where the individual domains intersect. I need to find out where do the domains of f and the domain, I'm using capital D for domain, and the domains of G intersect? That's my big question. So we'll go ahead and find them out. Our f of x in this particular case was the square root of 4 minus x squared. And what I see here is that I have to make sure that 4 minus x squared is greater than or equal to 0. I can't take the square root of a negative number. So I could go through it, and if I was to do this algebraically, at this point, we would have to use a sign analysis, which we generally agree is a pretty cumbersome process, and I would like to avoid that if I could. And in this particular case, I can, because I can make a recognition that this is an upper half semicircle with a center at the origin and a radius of 2. So I can make a real quick sketch of it and say, okay, that's -2, that's +2, that's +2, and I've got this upper half semicircle. So I can easily see that the domain of this function is the closed interval from -2 to 2. Done. So having those recognitions are really helpful because it saves you a lot of work. So that's our domain of f. We also need to find the domain of g. And g of x was, and I don't recall it, it was 3x plus 1. I'm having some orientation issues, it looks like. Was 3x plus 1. And if I look at that, I don't have any radicals, I don't have any denominators, it's a linear function, so its domain is all real numbers. If I want to look at this on a number line, -3, -2, just put a few values on here to help us out. The domain of f starts at -2, goes to +2. The domain of g is all real numbers. And since I'm looking for the intersection, I need to see where these two ideas, oh, that didn't go with it, where these two ideas overlap. So I'll just drag them up there. I take a look at it and say, well, the black line and the green line overlap starting here. That's not a great color. Starting here and all the way to there. So the domain of the addition is going to be from -2 to 2. The domain, but that's also the same as the domain for the subtraction, the domain for the multiplication, because they're all just the intersection. Now, I got to be careful on the division, however, that the domain of the division is that interval, but you'll recall from our previous work, we removed from that the number -1/3. We said x couldn't be -1/3. So I've got to take that out of the domain only for the division. Make those curly brackets nice, you know, because that -1/3, oh, that'd be right about there, will give us a 0 in the denominator. So that's a quick intro on finding, using operations on functions for specific values, in general cases to write new functions, as well as domains of finding those. So it can be some tricky stuff. We'll continue working on it, but this gets us a head start going into class.